Many times I have appreciated the work which is being done into the remote sensing, microwave remote sensing. Let us see today that how powerful the microwave remote sensing is. We have seen other remote sensing also, that remote sensing in visible band, infrared band, then micro thermal bands. So many bands remote sensing is possible, and each band, each set of the remote sensing have their own benefits and all other disadvantages. But this microwave remote sensing has gone so far, beyond the imagination. This is very useful, and mostly when we think of active remote sensing, we go for microwave remote sensing because it is far better than any other band we are conducting the remote sensing, capturing the data. Say, suppose when we are capturing data in passive remote sensing, depending upon the capacity of sensor, which we have seen in the previous lectures, that different sensor capture the reflected data in different bands, and depending upon the number of band available on the platform onto the sensor, we define the remote sensing as the monochromatic or the multispectral or the hyperspectral. So if so many bands are available, then which band is better? Definitely the microwave remote sensing is would be chosen. If you are investing money, then why to go for a feeble band which do not have that much energy to radiate and that much energy to receive back in form of reflected energy onto the sensor. So microwave remote sensing is almost having 100% transmittance through the atmosphere. So when we emit the energy from the radar system in microwave remote sensing, we know the wavelength varies from 1 millimeter to 1 meter. So that area, that wavelength zone, that wavelength section of the EMR, electromagnetic radiation, belongs to microwave remote sensing. And in this range, we could have passive remote sensing also, like the sun, if it's the source of energy, we could design our receivers. Receivers are called in this case as radiometers. We have seen the receivers or sensors onto the platform which sense the reflected energy. They are also termed as radiometers. Radiometers, radiations or thermal radiation from the surface objects, surface features, and being captured by the sensors. So those are also termed as radiometers, but radiometers does not represent the active radar system. Active radar system is having its own energy, whereas the radiometers receive the energy reflected, emitted by the sun or a source which is not onto the platform where the sensors or radiometers are mounted. So this is what is the big difference here between the microwave remote sensing active and microwave remote sensing passive. So microwave remote sensing passive radiometers are located and they capture the energy which is being reflected. Radar here is the active. Here they called radiation or TB, the thermal backscattering, and here the active, and we call it backscattering. This you can also understand as a reflected energy. Backscattering means when we transmit the energy. Suppose this is the source transmitter of the energy at the radar, onto the radar. So radar, what it transmits the energy, it propagates through the atmosphere, it reaches to the object, and after striking onto it, it gets reflected back to the antenna or the receiver, or you can say the radar system. So antenna is also there are the terms used here in the radar system, that the receivers are being antenna term is also used here. So this backscattering is nothing, almost synonym to the radiation, back radiation, or say reflection in the passive remote sensing. So I go further to understand it. that what is there into the. We have seen this EMR many a times, and we have seen that this transmittance here is very much high in the microwave compared to all other bands onto this. If you look at, then the visible is having the energy and also transmission, maximum transmission. And there are also transmission here in few bands, and we take advantage of while doing the remote sensing practices. But when it comes to that active remote sensing, when we have to design a system, then why should not go for where the transmittance is 100% here, like this. So this is what the energy levels here. This is for the natural light. This is for the natural light. The energy levels are very high, and energy levels are very high, and like this is going down here, and here in the microwave range, the energy levels are lesser. So if we make use of the passive energy microwave bands which are available in the passive energy or sun's energy, then what happens that the energy levels are less, so backscattering or reflectance is less, and in that case we have designed the satellite system and the mounted radar onto that, and everything happening as per, but only because that the sensor, the transmittance is natural, that is the sun, and the energy levels are less. So better if we have our own transmitter of the energy. So that is what is the active, that we for the better results we go for the active remote microwave remote sensing. Now, this is the microwave remote sensing. MRS is the microwave remote sensing. Advantages are so many, and these advantages will make you understand that why we wish to use the microwave band in remote sensing, especially when we are investing money in such projects of IRS satellites and sensors and creating so many things. Hundreds of crores rupees are going into the creation of all such remote sensing system. So let's look at the advantages of microwave remote sensing offers to us. That this remote sensing, this microwave remote sensing is a all-weather capability. It does have all-weather capability. Other like bands, if you go to visible or infrared or those things, then they are affected. If it is cloudy, then the EMR won't be penetrating in other bands. But in microwave band, the radiation would pass through, like this is shown here, that it passes through the clouds, come onto the Earth surface here, and it goes back. Even if it is raining in droplets like this, the EMR, the energy won't get absorbed by the droplets, and it will fall onto the Earth surface objects, and after reflection it will go back into the space back like this. So that is all weather capability. It is this is biggest advantage in many parts of our country, that areas are cloudy, say for more than 100 days. So in case of remote sensing, say we are not dealing in microwave, then what happens that for those 100 days when it is cloudy, we are deprived of the data. We are not obtaining the data from the system. So our system is not efficient. It is functional halfway, 50% of the time. So that we want to make it more efficient. It's workable all the time, all 365 days and 24 hours of the day. So that is what is the intention of capturing and collecting the data, because remote sensing is not only used for civilian purposes, it is also used for military purposes. Most of the uses, advanced uses of the remote sensing are into the military domain. So that is what all weather capability is having a bigger role to play in selection of microwave remote sensing. Day and night ability, say many times that when it's a daytime, then the electromagnetic radiation is having full energy levels, but during night the energy levels fall down, And if energy levels are not that much, then the reflected light which are reaching to the sun would definitely won't have that much amount. So signatures and signals are weak onto the sensor, and then classification, the processing will become difficult. Identification of the different movement onto the earth surface, different component, different land uses onto the earth surface can't be really processed. So that ability of microwave to work on day and night basis is also very important, independent of sun illumination. So that is what here, this is like when we have the active source of the microwave. Penetration through the penetration through a medium. Here you have seen that microwave radiation penetrates through the cloud and even the droplets of rain. And after reaching onto the Earth's surface, I will show you one chart here after a few slides, that even this radiation not only penetrating through the cloud and rain droplets, but it also penetrate into the soil media and into the snow. And we could really detect the changes taking place in the glaciers and also the soil moisture content for agricultural and irrigation purposes. So that is what is the advantage here, that it has a penetration through the medium. That it won't be absorbed by the medium, it penetrates and come back in form of scattered or back scattering or reflection. So that is what is the biggest advantage here of this energy. Information through microwave is different from the available from visible and infrared regions. Information through microwave is different from that available from visible and IR regions. That I have explained you that here the energy is high, and this information is clear-cut processing, and interpretation will become easy of the ground features which we are monitoring through the microwave. So that is what is advantage over the visible or infrared regions of the microwave. Remote sensing. Microwaves respond to dielectric and geometric properties of various features, which is not possible with the visible and infrared. So dielectric properties, you might have studied in physics that what the dielectric properties are of the features, objects of the surface. So they respond, these waves also give information about the dielectric constant and the various dielectric features of the object on the surface, and about the geometric properties. Since their response is sharp, we could also make it out the geometric properties, that how and where and in which shape they are onto the Earth's surface. So that the interpretation and classification become easy in case of microwave remote sensing, and especially in active microwave remote sensing. So I think you might be convinced with this these advantages to go for the microwave remote sensing and active sources of energy. This is how you could see at that the effect of cloud on the microwaves here, and this is the effect of rain on the microwave. So hardly any effect. Earlier, suppose this is a person transmittance, a transmission of this was the earlier transmission line, and when there is cloud, then hardly anything is being blocked by this cloud. So this much only, and rest of the thing is fully transmitting the microwave radiation. Here also, in case of rain, say earlier this was the graph here on the top of it, and if it is raining in the atmosphere, in the space, then what happens that the rain could deter this much only space, and rest of the space is having again the transmittance. So that is what is the effect of rain and cloud on microwave is very less, and they provide us the opportunity to work even when it is cloudy or it is raining on. This SAR is like a synthetic aperture radar. Synthetic aperture radar. APERTURE, aperture, synthetic aperture radar. So radar is what we have seen in the first slide, that radar is nothing but it's an active remote sensing which have its own source of energy. So R is radar. Synthetic aperture is an advanced version of the radar. So you can imagine that this X again is a modified version of SAR. SAR is a modified version of SLAR. We'll have look onto that why this SAR, SLAR, X.SAR, what these different names are. There are many times short note on this SAR and SLAR in university examination. So understand this, that while writing SAR, you should also explain the active remote sensing concept and principle, that how it works and why it is beneficial and how the data could be interpreted in more with more clarity. So that is what the SAR is. Am I audible?
Yes, sir.
Great. Okay. Now the effect of rainfall on SAR images, synthetic aperture radar images, is like that. This is without a thunderstorm and this is with a thunderstorm. But here the thing is that this is more clearer if there is no thunderstorm kind of thing. And this is an image taken or the data taken by SAR, synthetic aperture radar. And there is information available, but a little bit of haziness onto the screen. So that happens. But if we do the same remote sensing in thunderstorm, with the visible band or infrared band, then we could not make it out anything out of this. And even these clouds won't be appearing and we won't be interpreting anything onto the surface. So this is a kind of understanding it give us that what is happening in atmosphere, how the different phenomena are taking place. So that is what here for understanding is. Now the penetration of microwave into different media is this is a multi-frequency and multi-polarization. There are two kind of polarization: horizontal polarization of EMR. You might have studied the polarization of EMR in 12th standard, that horizontal and vertical polarization. There is a good sketch given of the electromagnetic radiation in the physics book. So that polarization, and if this is a multi-polarization and this is the multi-frequency. Multi-frequency how? Let's look at radar response to vegetation and subsurface horizons. How it, this is 3 centimeter, our microwave band, X band. If we are working in 3 centimeter range of the EMR, then it is called X band. Like if we are working in 6 centimeter, this is C band. If we are using 23 centimeter of the wavelength, microwave wavelength, then this is L band. And this is the whole thing coming up here and going back. Now let's look at that. This is the incident energy of the radar, active energy, and it strike onto the vegetation over here. This is leafy vegetation, and it can't penetrate through this whole canopy, all this leafy vegetable, and it can't reach up to the root zone here, but it will get reflected back, scattered from the canopy only, and will reach it. So this is the X band quality. What we are studying, we are understanding penetration of microwave. So in this X band, what we are looking at, the back scattering is taking place from the canopy. So if we are interested in knowing that how green is the forest, then we should use this band in understanding the remote sensing images or in interpretation the forest cover. Suppose we are using this 6 centimeter C band in the microwave, then the incident energy from the radar, this is the active energy, will penetrate further into the canopy. It will reach up to the down of the canopy and will get back scattered. So that is what it is. Likewise, this is a forest area and this is a barren land. Suppose this is a barren land. The same beam, the same wavelength 3 centimeter X band is incident onto this barren land, and when it is incident, you look at, then it penetrate into the top layer halfway, penetrate top layer halfway and back scattered and reaching back to the radar to the antenna and to the receiver, and then the data is stored. Likewise, it is penetrating this much, and here also onto barren land, if we are using C-band, 6 centimeter of wavelength in the microwave, then that penetrates the whole top layer here. Look at. And when we are using L-band, then this penetration is not only the canopy of the forest, but it reaches to the surface of almost onto the root area of the trees. So whole area would be covered. So these are very strong rays which are having good penetration. And if these same band, L band, is incident on the barren land, then the top layer is getting exposed. We'll get all the information here about what is available, whether there is available gold or moisture or aluminium in this top layer, or only the fertile land is there, or soil, or fine coarse sand, loamy sand. We could make differentiation because we are getting backscattered, and the different type of soils reflect differently. And so we could make it out that up to which depth, which type of soil is available here, or what is the content of the moisture. So very useful in agricultural field, these kind of penetrations and getting information interpretations. In multipolarization, you look at when this is incident, then it get mixed all through here within the object or feature, and then it gets back scattered, and we get the different sort of information in multipolarization in understanding the type of trees here grown in available in the forest. And likewise, this is also a multipolarization incident energy onto the soil and then going back. So this is a like polarized return, this dark one, and this is the cross polarized return given here in the sketches. I skip this slide. This again shows the penetration of the microwave when we are working with the microwave energy or microwave radiation. Then try to understand this graph, very interesting graph. Once you understand these values, this is volumetric moisture content in gram per centimeter cube. Gram per centimeter cube. So this is volumetric moisture here, and this represents the penetration depth. Penetration depth is this 10 raised to the power minus 3 means what? This is in meters. So 1000 part of the meter. So 1000 part of the meter is what? 1 millimeter. So penetration is 1 millimeter. Here 100th part of the meter means centimeter. This is 1/10 means 10 centimeter, and this is 1 meter. This is 1 means this is meter. So this much of penetration is there in of the radiation. And which radiation? This is soil. This is soil. Look at which one. This is megahertz, different 1.3, 4 megahertz, 10 megahertz. Likewise here, this is 4 megahertz, 10 megahertz, and 20 megahertz. Means this is 3 different wavelength and different frequency in the microwave region only, and they are having a kind of penetration up to what? Up to what? Up to 1 meter of the soil here, and up to the 30 meter of penetration. Penetration depth up to the 30 meter of the snow. Could you imagine this thing? So that much is penetration, and we get information like we can't really, while we are studying soil in agricultural sector or irrigation sector, we can't really dig up the soil and get the information all the time throughout the country. But here remote sensing, if we are doing with active radar remote sensing, active remote sensing in microwave, this is possible to get the information and process this data, and this data will become information and knowledge for farmers to grow different crops and have more product on their farms. So let's look at the active microwave remote sensing that we are discussing just now. I give you a kind of sense that how we call them as the active microwave remote sensing. The foremost requirement of this active microwave remote sensing, MRS, is that Active refers to a sensor that supplies its own source of energy or illumination. Supplies means sensor supplies, and in that case sensor is called transmitter of the energy. So energy or illumination, because sun illuminate the land surface, we also call it as illuminator. So it's not an illuminator, it is simply energy supplier transmitting the energy from the radar, and it's a transmitter when it is transmitting the energy. So that is what is the active here. Radar is an acronym to radio detection and ranging. So keep this full form of radar in your mind, that here the radar is an acronym for radio detection and ranging. You will ask that why the word or term radio is used when we are working in the microwave range of wavelength. We are not working in radio and TV wavelength range, but earlier this was used for the radio signals and that kind of purposes, and since then when we are illuminating, we are transmitting the energy, we call them the radar system, whether they are falling into the microwave region or into the radio wavelength region. So it is immaterial for us to for that 0.3 to 0.25 centimeter here radar system is most powerful, most energy efficient, and that is used into. So radar means radio detection and ranging. Likewise, if we are using laser wavelength, then it is called a light. Li is for the light. So light-based detection and ranging, remote sensing is based on the transmission of very short wavelength light, that is nothing but laser, and then recording the amount of light back scattered from the terrain. So this is for specific purposes. For oceanography we use, and this radar is having so many purposes for the topographical map creation of the surfaces and really mapping the farms and agricultural land and whole town and town planning, urban planning. Radars are used even to measure the rainfall. You might have studied in HWR that radars are used to measure the intensity of rain. So Doppler radars are there. We'll also look at them. And here, this is for especially for the oceanography that lidars are used, and these are nothing but the light detection and ranging lidar. And sonar you might have seen in the surveying 4th semester advanced surveying portion, that these are the sound waves. We use sound waves, and they are mostly used to measure the depth of water column in oceans and seas, which we are directly can't measure. So we use sonar, raise sonar wavelength of the electromagnetic spectrum, or maybe actively we are transmitting these sonar waves and then measuring the backscattered radiation that enable us to measure the depth of various points on the bed of the oceans. So I think you are comfortable with this system of radar, lidar, and sonar. All three you can consider as active microwave remote sensing. They are active remote sensing. Here we are having energy source onto our system platforms, and we are also having the receivers. So both you could consider all three are like this. Different radar system. We have seen active microwave remote sensing in the previous slide, and now we are looking at different radar system here. Different means within radar, how these radars are differentiated. Measuring vehicle speed like Doppler, measuring vehicle speed or Doppler radars. Surveillance like military and air traffic control. Like all these borders, we are doing surveillance, and major surveillance systems are being procured from Russia. India procures surveillance system from Russia. So what they are basically these advanced system of radar and plan position indicator radars PPI for military and air traffic control, and tracking radars and imaging radars are also there for the purpose which we were discussing for the terrain modeling, terrain mapping, terrain undulations. So tracking radars and imaging radars are also available. This is some of the kind of history and of the development of radar system. And this reads like that by the 1932, all these countries were having the radar system in place. So radar system, you could say, was developed even before remote sensing was not there. This passive remote sensing was not that much much developed. So remote sensing, we look at like it's only 30 into the domain. This radar system was before the Second World War. Second World War. It was being practiced in the advanced US, UK, Germany, and USSR that time. So radar were working in these countries by 1936, and they were tracking or monitoring or surveillance system used by these countries. And in 1950, this is mapping. This is for our use in the civil engineering use. Earlier, these were all military uses. 1950, a strip mapping radar, also known as side-looking airborne radar, SLAR. Earlier, I have given SAR. That was synthetic aperture radar. Here, A is different, airborne. A is not aperture, but it's airborne. So side-looking airborne radar is different, and this is the first development. And beyond that was the SAR was developed here in 60s and 70s. You look at. So this is the development of this active remote sensing, or say active microwave remote sensing. So SAR principle was pointed out in 1957 and 60s and 17. SLAR, side-looking airborne radar, and synthetic aperture radar were used extensively for Earth resources mapping. We are civil engineers and we are meant for these Earth resources mapping. We mostly deal with these kind of features of the remote sensing. Again, if you could define, if you want to divide, here we have divided into like 2-3 types, and then they can be also divided into type of signals we send on to the object for getting backscattering, like pulsed radar and continuous wave radar. Continuous wave radar means CW radar and pulse radar. So distance between, when we want to measure the distance between object and radar, then the pulse radar system is used. When we are interested in velocity, like what is the velocity of rainfall, intensity of rainfall, then the speed in which the droplets are falling from sky onto the earth. So that speed is measured, and you know this whole microwave is also part of light, and light, we know the velocity of the light is 3 × 10⁻⁷ So that is what is the thing taken into care of, and C is equal to V lambda. We use the simple principle of this finding out the velocity and also distance. So pulse radar is used for kind of measuring the distances between objects, and here this is for the measuring the speed or velocity between of the different objects. So velocity, many a times traffic engineering people, those who are like into the traffic offenses, are so they are having a kind of gun to punish the overspeeding vehicles. They use this continuous wave or continuous wave radars. This is explanation of the principle. We are not going that much into detail. I skip this too. I bring you to some of the early active sensors in remote sensing, microwave remote sensing. These are not Indian, but world over, which have been used in microwave wavelength or microwave band, you can say. So since 1978, the active microwave remote sensing is being practiced in US and USSR and Germany, UK. All these countries have been trying and deploying their vehicles in the space to capture the information about land, oceans, water, and military purposes. So these are some of the development shown to you onto this, that CSAT, ERS, JERS, radar shed, SIR, then NV set and the radar set. So you could imagine this is a Canadian sensor or the radar system, which is there, radar set 2. And likewise, this is CSAT is a US, and so there may be so many among these. I take you to one more slide and I will conclude my lecture there. These are some of the features, standard features. Now this is the last slide I'm going to take for microwave remote sensing. This will give you a kind of in-depth understanding of microwave remote sensing, because what microwave is. Now we look at here the centimeter wavelength, and this is the frequency. So we are least concerned about the frequency in microwave remote sensing or microwave remote sensing or remote sensing. We mostly use the wavelength as criteria to describe the remote sensing. So here 1.8 centimeter, I say the microwave is from 1 millimeter to 1 meter, and here 100 centimeter means 1 meter, but initially starting is 1.18 means 10 times. So in millimeter, this is 11 millimeter. So from 1 to 10 millimeter, there is no band available. Band designation, common wavelengths shown in the parenthesis. So band, understanding that how the band are formed. When we say multispectral, then there are say 15 to 20 bands around. When we say hyperspectral remote sensing, then there are 200 bands available, and we capture information and we analyze those remote sensing parameters. Now here in microwave, we are having so many bands. How many? K is 1.18 to 1.67. Then Ka is 0.75 to 1.18. Then Ku 1.67 to 2.4. Then X band is 2.4 to 3.2, and so on. If I go here, then P band is the last band, X, C, S, L, and P, 30 centimeter to 1 meter. So this P band is exactly 68.0 centimeter, but within that range, P and band designation. So radar wavelengths and frequency used in active microwave remote sensing investigations are these. And these you could understand that how, why, and where. So measure thrust is where we get full transmittance through the atmosphere. There is no atmospheric scattering of the microwave transmitted light, and also the reflected back scattering light. So that is what is the measured thrust, and we use only the the bands which are more competent, more efficient to give us information about the resources we are looking for. That is what is the meaning of this radar wavelength and frequency